Okay, so now we can really calculate sigma f is equal to a times n to the power b. We know what n is. We need to calculate a and b. And the formulas, let's put them back on the blackboard here. A is going to be equal to F, so 0.83, times our ultimate tensile strength, 770, 10 to the power 6 squared, divided by sigma E, which we just calculated, 160, 10 to the power 6. And so A is equal to 2,533, sorry, 53 megapascal.
Professor,
Yes,
could you go over how you found F again? What was on the x-axis?
sigma ut. So you just use sigma ut in kpsi, and then you can find your F. Okay?
Thank you.
B is minus 1/3 10 base logarithm of F 0.83 times sigma ut 770 divided by sigma E 160 10 to the power 6, and that is equal to minus 0.2005. So now using A and B, we can calculate sigma F, and that will be the numerator of our design factor there. Sigma F is going to be equal to 2,553 10 to the power 6 times 10 to the power 4, because that's our n, the life for which we're designing this cantilever beam. And then it needs to be raised to the power b, which we just calculated, minus 0.2005. And so sigma F is equal to 403 megapascal. When we get our result, even if it's an intermediate result, we do our little sanity check here. We're expecting this to be somewhere between sigma ut and sigma E, right? Sigma E would be for infinite fatigue life. The stress amplitude that gives you infinite fatigue life. We don't need to reach infinite fatigue life, so you expect that the fatigue strength is larger, greater than your endurance limit, which it is the case, right? So we got 403 is significantly larger than 160, because 10 to the power 4 cycles is a long distance away from infinite fatigue line, right? So that seems to make sense. And it is smaller than our ultimate tensile strength. That seems to make sense too. Yes? No, we always use the ultimate tensile strength even for a ductile material. We're actually currently working with a ductile material, right? We're mostly going to work with steels, and steels are by and large ductile materials unless they become exotic alloys. So you just use the sigma ut as it is in there in the formulas. Okay, so now we got to start working on our denominator there, sigma A. We need to calculate sigma A, and so we have this cantilever beam here that has a load F. So let's draw our moment line. Alright, so our moment line is going to be a triangle, where this is our maximum moment. And our maximum moment is going to be the force amplitude times the leverage arm, so that's going to be 2,000 times the leverage arm of 0.6. And so that gives us 1,200 Newton meters. We have, or we can then just write our equation, our flexure formula, so that is going to be M max times C, the maximum distance from the neutral axis, divided by the cross-sectional, or the moment of inertia of the cross-section. So let's fill in some values here, right? So sigma A is then equal to m max. What is the maximum distance from the neutral axis? B over 2. And what is our moment of inertia going to be of that cross-section? Is going to be width times height to the power 3 over 12. So it's going to be b times b to the power 3, b to the power 4, divided by 12, so I'll throw that 12 right away into the numerator. And then we can simplify this and say this is equal to 6 times m max over b to the power 3. And we know what m max is, so we're almost there. We can now throw everything we found into our original equation there. ND is equal to sigma f over sigma a. So what did we have set as ND? 1.5. 1.5 is equal to sigma f, which is 403, 10 to the power 6, divided by 6 times m max, which is 1200 Newton meters, divided by b to the power 3. And we can solve for b. And so b, if you solve for b, then you find that b is equal to 0.03 meters is equal to 30 millimeters. Okay. So let's take a break here. Does everybody understand what we've been doing so far? Does everybody follow me? Okay. First, and then you.
So you picked sigma A based off of the loading that you were using?
Yes, I mean sigma A needs to reflect loading. This is a case of simple bending. So the maximum stress occurring in the design is going to be dependent on the type of loading that you have. This is simple bending, so we used the flexure formula to calculate the stress. Yes?
Where do we use the T strength to calculate the 160 MPa? Where does that come back into play?
That's a... Oh, that wasn't the fatigue strength, right?
Or sorry,
The endurance limit was 160, right? That comes into play when calculating our fatigue strength. Right? So we find a value that is larger than the endurance limit because we're only needing 10 to the power 4 cycles, not 10 to the power 6, which is the equivalent of infinite fatigue life. Yes? Who was first?
I'll just go quick. So we have two b's here. We have a b that's a side length and we have a b that's a coefficient. Which is which in our calculations here?
Oh, yeah, so you have to keep track of the parameters here. B is the side, this is what we calculate here, right? So this is the design parameter. A and B here are just parameters that are called the same as in the textbook and in the formula sheet, and they're different from this A and B. Right? So you've got to really keep track of your parameters here. We don't have enough letters in the alphabet to name each parameter that we use differently. There was another question over here. Yes?
So now that we have those values, how are we going to go back and check KB?
That's the next step. I just wanted to make sure before we did that everybody is on the same page. Right? So we started from our design factor. We said it's the fatigue strength divided by the maximum stress occurring in the design. We calculated sigma f based on our endurance limit. Right? We get sigma f. Then we say, okay, what's the loading situation here? It's pure bending, so we can calculate sigma a using the flexure formula. We start from the definition of our design factor, we plug in all those values, and we find the unknown design parameter b. Now we're going to go back and check whether and that's the end of the problem then, we're just having 2 minutes left here, so we'll have just finished this problem here, but now we indeed got to go back and check whether we made the correct assumption over there. Is this KB assumption, was it a good assumption? Alright, so we need to calculate, we need to say, check KB. For that we need to calculate an equivalent diameter, which is going to be 0.808 times B is 0.808 times, and we need to put it in millimeters, so times 30 is approximately equal to 24.24 millimeters. That's our equivalent diameter. And now the equivalent diameter gets plugged into these formulas over here. 24 millimeters is in between 2.79 and 51. So we're going to say KB is equal to, what's the formula, 1.24, the equivalent, and then raised to the power minus 0.107. And so you got 1.24 times 24.24, because we have to plug in our diameter in millimeters, and we raise that to the power 0.107, and we find that KB is equal to 0.88. So we made a good assumption. If we were to find a KB value that is significantly smaller than 0.85, that means that we were not conservative enough when assuming KB. And so we have to go back to that new KB value that we found and redo our calculation. If we find something that is, say, 0.95,